I want to make this video to give you a brief overview of R and its essential features so you're better prepared for our first research activity that deals with Monte Carlo simulations. I want to begin with answering the question, what is R? What is this thing that we're learning about? And I'm going to write a definition first and then I'll explain it. R is an interpreted programming language that is primarily used for data analysis. So it's a programming language. We should know what that means. What that means is it has, like any language, it has its own rules, its own grammar that tell it what things mean and how we need to specify it to it in order for it to do what we want. As an example, in Python, the grammar of Python, the sort of syntax, when we want to create a function, we use the def keyword, the def, if you remember, and then we put in the name of a function here. That stands, in Python's language, in Python's grammar, that stands for define a function by that name. Similarly, in R, we have other conventions we have to follow in order for it to behave the way that we expect. Its primary use, as we can see, is data analysis, which indicates that it has a strong basis in statistics, so it's good to know that that's our application area. But one part of this definition that I think is not intuitive is interpreted. What does that mean in the context of a programming language? What interpreted means in this case is that it executes code line by line. And so the advantages of this might be readily apparent, but when I say it executes line by line code rather than all at once, what I mean by that, I'll show you visually, is that if we had 4 lines of code here, it'll execute 1, then 2, then 3, then 4. So the execution direction is like this. And the primary advantage of that is it allows for easy experimentation. We can make a change at a particular line and just rerun that line, and it gives us a different output. And that's very useful for learning. We couldn't really do that if we had to make a change, make an entirely new file, compile that file, if you heard that word before, and then open that new file. That would be very tedious to make small changes, and it wouldn't really be conducive to learning. Another huge benefit of it being interpreted is that errors are encountered as we run the code, as they come about. What I mean by that is, since we're running everything line by line, let's say there's an issue on line 2 right here. Something is wrong. What R is going to do is when it hits line 2, it might spit out something like this. Error, line 2, and some error message that describes the nature of the error. And this is usually very difficult to understand if you're not familiar with the intricacies of programming. But the main point here is that it'll indicate an error, it'll indicate where it occurred, and it will not run this line or this line. It'll stop here. It'll stop the execution here. And so we can know, hey, there's an issue right here, so let me go into that line, see what that issue is, and fix it in order to make the code run as expected. So that's what R is. The next question that I want to answer is, why R? Why are we using R? Why are we not using something like Python? Or why not use a language like C or C# or Java or whatever? Well, there's a couple of advantages. The interpreted nature is a huge one, as I mentioned earlier, but some other advantages are that it's open source and free. Free meaning that I could download it whenever I want at no cost to myself, no subscription plan, nothing. I could just download it and use it. Open source referring to the fact that the code used to build R is available online for anybody to see, edit, modify, and distribute completely freely. And this encourages a community to build around this, a community of people, of developers, that want to add extra features that they find useful to the software. For example, let's picture a community of statisticians. Let's say they want to do something complicated, polynomial regression to develop a safety performance function. That might not be something that's available in R to begin with. So they could use what's available in R to create their own set of tools that allows them to do that thing, modify it, redistribute it, and that now becomes part of the standard of R. And that's something that becomes available to us. And that's huge because that means that it's currently actively being worked on and actively being exposed to new features that support almost any kind of analysis that we could want to do, which is why it's so prevalent in the field of data analysis. The second point, a pro for R, is that it's available on every OS. And OS stands for operating system. So what I mean by that is Windows, Mac, and Linux. All three of those can run R, and they will run the exact same way on all three. A piece of code on Windows in R will run the same way on Mac, same way on Linux. The third point, and this is a huge point, is that it has an extensive library of freely available tools which extend its functionality. And briefly, what I mean by that is because it's open source, developers are creating these tools, these things that we can access for free that allows us to do something specific that might not be available in R to begin with. R comes with some sort of tools out of the box, sort of what we call base R, but not everything, of course. If we're doing something very specific, like working with some sort of package that deals with traffic engineering, we might have to install that separately, and that's something that R lets us do for free, and it exposes new functionality to R that allows us to do our particular type of analysis. That's huge, because what that means is that if we know the library and we know how to use it, we can do more with the same product that's freely available. That's not necessarily something we can do with a commercial software like Excel, for example. In Excel, there might be some sort of analysis we want to do, but it might not be possible. Either we might have to do some very complicated coding to do it, or it just cannot be done. With R, often it can be done, and in a much easier way. And the final point here that I want to mention is that there's an extensive help network surrounding a lot of R topics. You'll see this if you Google around, and even built into R is a help where it has a lot of detail, a lot of description on built-in things with R, built-in data sets, built-in functions, how to use them, what they expect as inputs, some examples of their use cases, what's related to them, what are some instances that they can be implied in, or, for example, what are some procedures that I can follow to achieve X, Y, Z, or analyze ABC data. There's a huge amount of help available, and it's very detailed and very thorough. And that is incredibly useful for learning because that means that we can hit the ground running, essentially. Now, that's all well and good, but I would think, just to keep it simple, there's one main advantage for us that I want us all to keep in mind. R lets us do this. It lets us have a repeatable code of procedures. What I mean by that is this. If I have some lines of code here, let's say this is R code. This serves as a permanent and accurate record of every decision I made to analyze some data or to solve a problem. That data, these decisions can be shared with somebody else who can look at that and understand, are these reasonable assumptions that this person made? Is this a reasonable and logical and rational process that this person followed to solve this problem? What did they assume? Where did they get this data? Is it reasonable to assume that? Why did they do this analysis? Why did they use this tools instead of these tools? And questions of that nature come about, and it allows us others to understand our thought process very thoroughly. especially for our professor to understand why we did what we did. The ultimate goal of doing it in this way is that it's collaborative. If I solve something in a way that's really unique or really useful, and I give it to somebody else, they might say, I really like the way you approached problem A. I can apply it to problem B in my own field, and suddenly you've solved a problem for somebody else, or you found a way of approaching a problem they didn't have, which leads again to a solution that didn't exist previously. Now, in terms of accessing R, there's a lot of different ways we can do that. But primarily, for R, we can access it through a portal known as CRAN. So again, R is available through a portal called CRAN. CRAN, in this case, C-R-A-N, stands for Comprehensive R Archive Network. And we can even look for this in a new tab here. If I look for CRAN R, we'll see that our first link here is cran.r-project.org. And if we open that, we'll see that we can download R for Windows through here. Once we've done this, once you've downloaded R and installed it through the installation wizard, we can check its installation by opening up and searching for R. In this case, I have version 4.4.1. And when I launch it, I get something called the R GUI, the R Guided User Interface, which makes it easier to work with R. But you can see all we have is just this area that we can type in something. It's really confusing looking. But just to make sure that it's working, let's type in something like 1 plus 9 and hit enter. You'll see the output of 10. You'll see this bracket 1. Don't worry about what that means right now. I'll cover it at a later point. But we see that 1 plus 9 gives us 10. And what that means for us, logically enough, is that R is installed properly and working as we expect. So let's close it for now. The next piece of software that I recommend we get is RStudio. And RStudio, we can get it from posit.co. So posit.co RStudio. And that'll take us to this link here. Posit.co downloads RStudio IDE. And we can simply download it for the particular OS that we need. Now, you saw on that page it called RStudio an IDE. What does that mean? It stands for Integrated Development Environment. And the easiest way to think about what an IDE is sort of like an add-on to R, that it gives us a lot of nice and handy bonus features that makes working with R a lot simpler. You'll see this when I open R, but these include features, RStudio I mean, features like the R console, a script editor, a file browser, a plot viewer, things that are possible in R, but that are much easier to do in RStudio, and that speeds our job up as developers, which is why we tend to use it. With that, I want to give an overview of RStudio. So I've already have it installed. I'm going to launch RStudio. And I'm just going to pause until it opens up. So when you first open RStudio, which I have open here, you might see something very similar to this. You'll have 3 windows or panes. On the left here, this one with the blinking cursor, this is called the R console window. This one on the top right is the environment pane. And the one on the bottom right here is the files or plots window. So let's explore RStudio a little bit. First, we can customize it. So we can change, for example, how these panes look like. So in order to do that, up at the top at the menu bar here, we go to Tools, and down at the bottom, we select Global Options. So it's going to open up the Global Options window. And here, if we go to Pane Layout, we can change, for example, where these things are located. So as an example, let's put the console up here and the environment in the bottom right. And if we click Apply, you'll see the console is here, environment's here, files are here. I won't worry about this right now. I'll explain that later. But let me go back and just change that to its default because I think it looked better before. So we can do that. Another thing that we can do when we're here is we can change the theme to make it a little bit easier to see. We might find it a little bit hard to look at this light theme. So in order to, again, we can do that under Tools, Global Options. But in this case, instead of clicking Pane Layout, we click Appearance. And so here we get some options for theme, zoom level, editor font size, but editor theme right here. So I can click on these and preview what it will look like. Let's say I like this one. I click OK or Apply, and there we are. It's changed everything to be dark with green text. While I'm here, I'm going to change my zoom level to 125%. Just to make everything a little bit easier to see when we're doing this tutorial. So now let's discuss each of these particular windows here. Let's begin with the console window. This is our powerhouse. It's where R is going to evaluate and run the code that we write, and it's where output will be printed out from R. We can actually provide our code directly into the console right after this right arrow icon here. We call that the command prompt icon. And actually, we saw that earlier when we opened up the R GUI. But as an example, let's type in 2 plus 2. And if we hit enter, we get the output 4. So R is working as a calculator. That's great to know. Again, I'll explain later what this 1 means. But here, as you can imagine, we can try something else. We can try 3 times 9, 27, or 36 divided by 6, 6, or 2 times 3 times 8, 2 times 3 times 9, which is 54. We could do a bunch of math like this. But as you can probably imagine, it isn't really efficient to run code this way, and becomes very tedious when we have to do something a little bit more complicated than multiplying 3 numbers together. An alternative approach here is to use something we call an R script. And R scripts are just plain text files that contain our code that we write, and that they have an R.R extension. So when we write an R script, every single line of that script where we write our code gets fed or provided into the console line by line to be executed. Because as we mentioned previously, R is interpreted. It has to run line by line. In order to make a new R script in RStudio, we go to File, New File, R script. And you'll see that it opens up a new window here. And this window is called the source window. It's added to the top left right here, as you can see. And this window is really where we're going to edit our scripts and where we're going to write our entire code. We write our code in this window, and then we execute it, and we get output in the console. That's now been pushed to the bottom left. Now, in order for the code to be sourced or pulled from this window to the console, what we have to do is place our cursor, our mouse cursor, at the beginning of the line and just push run, and then it'll feed it into the console line by line. So, sort of as an example, let's put 3 plus 3, put our cursor here, and hit run, and you'll see it's sourced 3 plus 3 down here, and it gave me the output of 6. And now, this is unaffected here, so we still have a record of this. So if we wanted to show somebody, hey, I did 3 plus 3, we can do that. And again, this is why R is so powerful. We have this reproducible set of actions that we made that serves as a permanent record of the decisions that we made. For now, though, let's just delete this because it's kind of not really useful. Also, notice one thing. When I type whatever, you see that this changes color slightly, and it has a little asterisk here. What that means is that changes have been made and the file hasn't been saved. And so it's R warning me to save the file so that I don't lose the work that I've done. In order to save files, we can do File, save, and it'll save the file, or save as to save it as a different name, or the keyboard shortcut Control+S. While we're in this menu here, we can open files by going File, Open File, or using the keyboard shortcut Control plus the letter O. Now, again, I said R scripts are just plain text files. So what that means, really, is I can open up a notepad, and I can look at it in Notepad. There's nothing particularly special about it. It's just something that R understands to work with, and it's a very efficient way of storing this text. So that's what console and source are. What about these two over here, environment and files? The environment, history, and connections, and tutorial. These are all different tabs that we can click on that expose different things to us. Environment holds the things that we make, which are called objects, in the current global environment. We can see that here, global environment. So that can include stuff like any data that we import into R, or values that we save, or functions that we use, and so much more. And we'll see that a little bit later, but anything that we make or do will go into this environment. We can display objects in the environment in either list view or grid view just by changing this here, and we can explore later what that does. And we can remove or clean our environment by pressing the broom icon here. Now, be careful with this. This will wipe everything. And what that means is if we had something by a name here that we were using, some sort of data, if we click this and it wipes it, it's no longer available. And we have to put it back in the environment again. History, if we click on history, it shows us all the commands we entered in the R console. So we can see, for example, some previous commands I entered, but also stuff like 2 + 2 and 3 × 9, the math operations that we did before. And we can browse this actually to see what did we do previously, and maybe find a piece of code that we entered before that we found very useful but we can't really remember. And if we actually click on it, double click on it, we can bring it into the console and run it again. Now, it isn't super common that we'll do this. It's very seldomly used, but it's a feature that we have available to. And we can actually move it to source or console. So for example, I can move this to the source and then run it again from here. And you'll see that it updates down here as well to show that it's been recently run. I'll remove that for now. The connections tab here, this really just lets us connect to external data sources like a database that's outside of an organization. That's not something we'll worry about right now because I just want to expose you to the base R features, and that's something that's a little bit more involved and advanced. Now, let's turn our attention to the bottom right here with the Files, Plots, Packages, Help, Viewer, and Presentation window. Files here, you can think of it as sort of functionally equivalent to Windows Explorer. It'll list every single file and folder, and another word for folder that you hear all the time is directory, in the current working directory or current working folder for your particular PC. And, excuse me, we can move stuff around here, we can create new files, we can create new folders, we can rename stuff, we can open stuff directly from here, and we can delete things from here. Essentially the exact same way you would do it in Windows Explorer, we can do it here. As an example, let me click on here to create a new folder. It'll prompt me for a folder name. So let's just call this Made in RStudio and hit Enter or OK, and you'll see that it pops up right here in Home, Semester 6, Stats, R root, which is our sort of directory, our current working directory right now. But let's say I made a mistake. So I can click on this, go rename. Okay, what's the name you want to rename it to? So let's say I said rename in RStudio. And hit OK. You'll see now that name has changed for that particular folder. Now let's say I want to get rid of this folder. I just click on this little checkbox and go delete. That'll ask me, do I really want to delete it? I say yes. And now it's gone. And so we can do things of that nature with files. Plots here is empty right now, but it's where we would see any sort of plots that we make in R. It would be displayed here. We can zoom here, and we can export it to other formats like a PNG so that we can use it in reports, for example. This is something we've been exposed to in class with the ggplot, and also with some sort of built-in functions in R that can do plotting. But again, because this is sort of an advanced topic and sort of beyond what we're after, I won't cover it at this point. The Packages tab here will list every single package I have installed on my computer. And this will differ depending on your installation, depending on the packages you have. And in this case, we can install new packages and update existing packages right from this window. And we can actually scroll to see the sort of packages I have installed. And you can see I have a lot of them installed. I can see a description, the name of the package, its description, its version number, its source, and I can checkbox the ones I want to update and hit update or install to add new ones. There are alternative ways to do this via code, but again, we won't really explore that at the moment. The next tab is Help, and this will show our documentation for any particular code we tell it to. So we can actually here go browse by particular topics, or we can search here for a particular topic that we're after to get a sort of help file for it. So for example, let's search for regression, if we can find it. Or let's click on R and Stack Overflow. And it'll come up to Stack Overflow questions tagged R, and Stack Overflow is a community of developers that we can use as a resource to find answers for common questions in R. And these are answers from professional developers that can help us if we're stuck with a particular problem. Now, I don't want to talk about viewer representation. They're not incredibly useful for us, but just the main ones that we have to keep aware of are files and plots and potentially packages, but particularly files. Now, as a quick little bonus, if you click this broom icon here, we can clear the console, make it a lot easier to work with. Let's talk now a little bit more about our packages. I mentioned them before, but what is a package? You can think of this as essentially a collection of functions and data and help files that someone has assembled into a really well-structured way that we can install and use. So for example, in class we use tidyverse. Tidyverse is a collection of a bunch of functions and a bunch of data sets and a lot of help files that are associated with that data that some other team of developers have made that we can use to make nice looking graphs, for example, or do really complicated filtering of data in a much easier way than we could in base R. Most of the packages that we're going to use are coming from CRAN, the Comprehensive R Archive Network. Packages, as I mentioned earlier, extend R's functionality so that we can do more with R. We can install new packages from CRAN in code by running the install packages function, and we pass in package name as the argument. So, as an example, we can do this. Install packages tidyverse in quotes. It's good practice to put it in quotes, and if I hit enter, it'll say where it's going to get that information from. You can say here RStudio.com, where it's going to download it to its size. You can see here that it's downloaded it and where that download is now placed in. I now clean the console just to make it easier. We can also add to that install packages function an argument called dependencies and set it to true. What that will do is it'll install every additional package that the package we are after requires to work. So let me explain the logic here. Let's say we have two packages, package A, package B. Let's say package A has a function that converts Fahrenheit to Celsius. It's a very common thing to do. Let's say package B is a weather application. It will let you search for a location on Earth and it'll print out its weather on that particular day. Package B depends on package A's conversion function to go from Fahrenheit to Celsius or Celsius to Fahrenheit. So if package B depends on that conversion function, then in order for us to use package B, we also have to have package A. So when we set dependencies equal true and install package B, it will also install package A because package B is using a function from package A in order to do what we expect it to do. In order to update packages, we can run the update packages function. Again, in this case, we can just use, we don't have to provide an argument, but as an optional argument, we can provide ask equal to false. And all that will do is make it so that we don't have to agree to every new installation of a new package or upgrade of a new version of a package. So it makes it easier for us to update everything. Let's run it actually, so I can show you what I mean. Update.packages, and then ask equal to false, all in uppercase. And I'll hit enter to run it. You'll see this coming up. I'll just hit no in this case. Get an error. So let's try running it again, saying yes to that. And you'll see that it's downloading all these packages. And you can see now this what have been updated. Everything's updated. Everything's up to the most recent version possible. So that's how we run update packages, to update everything that we have installed. Once installed, once we have a package installed, we can load it or use it by running the library function and providing the package name as an argument. So what I mean by that is library package name. And R is very nice, RStudio is very nice. It'll try to autocomplete for us, so that makes it easier for us to type. Here, what this will do, literally, is just make everything from package name available to us. And library, again, like I said, is a function that loads the package and any other packages that that package requires in order for it to work. And you have to run this every time we want to use that package. Common practice in this case, since we have to run it all the time, is to put it at the beginning of our file here. So put it right at the top here. So library tidyverse, for example. It's a common thing to do. And then have some code down here so that the first thing that's run is the code that sets up the package that we have installed, so that we can use it later on in our file without having to mix it in with everything else. I won't really get much more into this. It's very complicated, as you can imagine. We can go into a lot of detail, but I think this is perfectly fine for now and gives us a good enough understanding of the nature of packages. Now, there are some options to create a project in RStudio. I won't really go into that. That's more of an advanced topic, and it's not super useful for us. So let me go into the next task here, which is setting the current working directory, the CWD for short. This is where R will look for files to load and where we'll put files that we save by default. And we can see that it's shown at the top here in the console here as the ~semester6/stats/rroot/. That's our current working directory. We can even print this out by running the get working directory, getwd function, hit enter, and you'll see that that's my current working directory. You'll also see that this tilde thing is short for C users Alexristic documents. So that's a good thing to keep in mind, that it's a shorthand just to save some space. Now, without a project, we need to set this ourselves. We need to set our working directory using the setwd function. And in order to do that, we have to provide an absolute path. And what absolute path means is we have to provide a specific path from the beginning of our file system to a particular folder. To show you what I mean, I'm going to open up Windows Explorer here. I'm going to go to Music here, or even a folder like documents, OneNote, notebooks. So if you click on this, this is an absolute path. It says go from the C drive to the users folder, to my username folder, to the documents folder, to OneNote notebooks. It specifically, explicitly says go from that to that to that to that. Go in that particular structure. Go from A to B to C to D. We have to provide a path like that if we don't use projects. And I wanted to mention that first as a reason to motivate why we're going to do projects, because if we use an absolute path, for example, C users Alex Ristich, documents semester 6, stats are root, that only works on my computer. You don't have on your computer a folder with that name. Or I'm assuming you don't. And what a complication of that is if I share something with you, it won't work because I use an absolute path. But if I use an R project, I can do a relative path. I can do a path where essentially what that means is there are folders that are relative to one another. And in this case, it's relative to what's called the root project directory or root project folder. All that is to say that if we make a project, an RStudio project, and share it with somebody, it will work on their machine because the information will be relative to that directory, to that R root directory that we provided them. So, okay, how do we set up an R project? What do we do? Well, in order to do that, and another thing I will mention is that projects have their own workspace and their own source window here, and their own environment and their own history. What that means is that we can have two different instances of RStudio running that are completely isolated from one another, so that you can work on one problem in isolation, so one sort of set of things without impacting something else. So let's go through making a project just to make this more concrete. We'll go to File in the upper left here and click on New Project. And just give it a second here to load. I'll pause and I'll come back once it's loaded. Okay, so we're presented with this here, the New Project wizard. And in here, I want to create it from a new directory. So I'll click the first option, New Directory, start a project in a brand new working directory. The project type is going to be a new project. There's a lot of options that we have here, but we want a new project. And here we can just specify the root directory name. So let's call this my first project. And this is going to be a subdirectory, meaning a folder underneath a folder of, right now, C users Alex Ristich documents. But we can, of course, browse to change that. We can say, for example, oh, it's going to be in semester 6. And so this is going to create it as a subdirectory of this. Final thing that we need to do here is click this to open it in a new session and then go create project. And I'll pause once it does this. And so here's our new session of RStudio, or our instance. And we can see the title is now my first project. We can see the working directory is now my first project. And we can see a new folder called myfirstproject.rproj. This actually is a shortcut. If we navigate to that folder, if we go to my documents and semester 6, we can actually click on this folder. We can actually click on this to open this up in RStudio very quickly, or we can even click on it here to open it. But since we already have it open, there's no real point in doing that. So let's customize our project a little bit here. Let's go to Tools, and now Project Options, because we're working with a project. And under Project Options in general, all I want to change is these two. Restore our data into workspace at startup, and save workspace to our data on exit. Set these both to no. What that will do is it's going to ensure that we always have a clean R session whenever we open the project, rather than saving something and then opening it up later, which might create some complications later on. So hit OK, and that setting is now applied. So let's go into now what I mean by relative paths very quickly. So I'm just going to pause and I'll be right back. When I say relative, what I mean is that if we wanted to share this new project now, all we have to do is copy this here and give it to somebody else. And if we wanted to use a relative path, I'll illustrate this by creating a new folder. Let's call it raw data. And in raw data, let's make a blank file, call it a text file, and say it's test.txt. Doesn't really matter what it is. But if we look here, this is now my root directory that has the R project file. Raw data is a directory within that. And so when I say a relative path, let's say I had a function called open that opens a file, I can just type this, open raw data test.txt. This is now going to be relative to the R project file directory, and no matter where the user puts it on the system, it's always going to be relative to that, and it's always going to search here, here, and open that file as we intended to do. Let me pause real quick. Let me just show you if we didn't use this, what we would have to do. If we didn't use this, we'd have to do something like this. Set WD C users Alex Ristich documents Sem6 my first project raw data test.txt. We'd have to put in all of that in order for us to open that file properly without an R project, which, as you can imagine, is much more cumbersome and also, like we mentioned, not able to be shared. So that's why I would recommend strongly to use R projects. It isolates things, makes it easier for us to work with. And similarly, be careful about you creating folders. You don't want to have garbage all over. I recommend having a folder to hold data. Unprocessed data, a process data folder, a data for your R scripts, the code that we're writing, and maybe even a folder for outputs if you're outputting, for example, plots or other sort of data. Now, I want to now pivot a little bit to talk about some essentials of R. We've talked about RStudio a lot, but now let's talk about the R language itself. Before we do that, I did remember a few little nice things I want to mention in RStudio just before we move on from the topic of just RStudio. The first thing we could do is write in TS. And then if we hit Shift Tab, we can convert this automatically into a timestamp. Sunday, October 13th at 4:43 p.m. 2024. Pretty useful if we want to create something at the top of our code that shows when we created our script. If we wanted to uncomment or comment multiple lines, and comments, by the way, I'll show you. If we go here, go File, New File, our script. If I write some code, 3 plus 3 times 5 minus 4, comments we enter with the pound sign, this symbol here. And again, this might be a little bit hard to see, so let me go back to not global options. I want project options here. So if we go to Tools, Project Options, and go to Code Editing, or actually, sorry, I meant to say Global Options because this is something that affects RStudio globally. If we go to Appearance, let's just zoom in a little bit more just to make it easier to see. This is not really working too good for me because my screen is kind of small. So just bear with me here while I sort this. I'll pause and I'll come back. Okay, there we are. All I did was I just changed the font size to 16. But comments, as you can see here, are indicated by this hash sign. And then we just type in whatever we want. And these are not run by R. This is just something that we put in for ourselves to explain what we're doing. So for example, here I could say testing PEMDAS for order operations. But let's say now we had a lot of code like do X, do Y, do Z, and do P, and so on. And I was doing something and then I want to comment that all or uncomment it. What I can do is I can select all of this and then go Control Shift C. And it'll comment all the lines, meaning that they won't run. Just to illustrate that. Run, 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 run. Nothing happens. Again, I can also undo it by selecting all of it and going Control Shift C, and now they're all uncommented and they will run. So that's just some handy things to keep in mind. Another thing I will mention is for our assignments, we sometimes have to cite R. And in order to get a nice citation of R, we just type in citation and hit enter. And there we are. To cite an R, we just use this. And we copy that over, and now we have a citation for R that we need, just by using the citation function. So that's all about RStudio that I want to cover at the particular moment. Now let's get into the specifics of R, the language. So first off, R is case sensitive. So what do I mean by that? I mean this. If I have a thing called dog, that is not the same as dog, and that is not the same as dog. Similarly, ANOVA in lowercase, ANOVA in uppercase, ANOVA with a number, these are all different things. These are three different things, these are two different things, and just be careful with that because it's easy to mix that up and miss that feature. I mentioned the comments already. In terms of entering code, maybe you've seen it already, you enter whatever code you want. So code line 1 on one line, then you hit enter to go to the next line and go code line 2, code line 3. There are other ways of entering code with multiple lines of code per line, but that's not considered good practice because it's very hard to read and very hard to fix. So whenever you have a new line of code or whenever you want to execute some new code, just put it on a new line. This can go on forever, realistically. Also, by the way, what I'm doing there is just going Control A to select everything and backspace to go back to the first line. If you're ever running R and you see an icon like the plus whenever you run some code, that's called a continuation prompt. That will appear if you haven't completed some sort of code and R is waiting for you to continue, to finish it. And really all you have to do there is just fix the typo. We'll see that a little bit later when we deal with some more detailed R things, but just keep that in mind. Now, I want to go back to this. I'll go back to the console here. 2 plus 2. Say I got 4, but I also got this bracket 1. What does that mean? The bracket 1 means that this observation of 4, the number, the observation number, is at the start of the first observation. Really, we only have one answer, so of course it's always going to be the first. It's sort of like the position of the answer. This doesn't really help us unless we have multi-level of data. If we have something that has multiple rows of data, then this number might go from 1 to, for example, 6 or 11 or whatever to indicate that that's the 6th number or the 11th number or the 15th thing that we're looking at. So that's all that really is referring to. As we saw earlier, R is a very good calculator. We can do stuff like that. We can do stuff like this. We can do division. We can do order of operations. All of that is supported in the sort of standard way that we'd expect. And we also have a lot of built-in functions, like I mentioned. For example, logarithm base 10, 100, 2. So, 2 to the power of 10. 10 to the power of 2 is 100. That's what that's referring to. Or we have exp to raise e to the power of something. So e to the power of 2, 7.389056. Or we have square root to get the square root of something. So square root of 36 is 6, because 6 squared is 36. We have mathematical constants like pi, 3.141593. So we can use that to, for example, find the area of a circle. In order to find the area of a circle, which has the formula pi r squared, pi times r squared, we have to know that we can do something squared. So in order to square something, we can do the number, hat symbol, and the power. So in this case, 3 to the power of 2, or 3 squared, is 9. So let's find an area of the circle that has a radius of 3. So in order to do that, we go pi times 3 squared. And the area of a circle with a radius of 3 is 28.27 in whatever units we're measuring area. Let's say this is square millimeters. Now, that's all well and good, but that's not something that can really build into a lot of complicated features. We really need to discuss our objects. And this is a really powerful thing. But our objects really can be pretty much anything. They can be numbers. They can be a piece of text or a letter. They can be plots or graphs. They can be functions. They can be time series. They can be a lot of things. And each one of these has a particular data type. So, in order to create an object, all we have to do is assign it a name. So when I say that, what I mean is that we bind a name to a variable, to a value, using the assignment operator. We create an object by binding a name to a value. So when I say binding a name to a value, what I mean is this. A value would be something like 33. That's a number, that's a value, that's something that we can understand. Or the word apple, that's a value. A name might be something like favorite fruit or lucky number. These are not things that R understands by default, but that are names that we can use to make more sense of values. And when we bind a name like that to a value, using the assignment operation, we create a object. So, simple example. Favorite number, and the assignment operator is the less than and a hyphen 4. Run this, and you'll notice some things have changed. So, first, we can see that if we want to see an object's value, we can simply type in its name. Favorite number, we get output 4. So now we have a name to refer to a value, a name that might be a lot more useful for us than 4, for example. In some context, 4 might mean nothing, but favorite number in the context of a application that calculates lucky numbers or birthdays makes a lot more sense. Now, you might have noticed that the environment window changed. When we create objects, they're tracked in the session of RStudio that we're using. And when I say they're tracked, I mean that as they are added, they change in the global environment. So we can see here, for example, that we have the name of the object and the value it's associated with. And we can make that even more clear by changing this to grid. So we'll see that that's favorite number. It's a numeric type. It has a length of 1, and its value is 4. And that's its actual physical size, 56 bytes. If we go back to list, again, we can see favorite number is 4. So now we know that this value in the environment is associated with the number 4. And we can use this value, we can use this object, we can use this name, this variable, instead of the particular value it refers to, because it's functionally equivalent. Now you also saw that it's a numeric data type. There are other data types, like character, which is used to store text. And when we store text, we put it in quotes. So for example, my underscore name, assignment, Alexander Ristic. Run that. We see this. And if I go to grid view, my name, type, character, length 1, value, what I typed in, and size is a lot bigger than the number, which makes sense because there's more data stored there, essentially. And of course, like I noted previously, when we use text, we enclose it in quotes. So what happens if we don't do that? What happens if I do this? What happens if I create a new line? Say, my new name, Alexander Ristic. What do you think will happen when I run this? I got an error. Unexpected symbol. So what does that mean? In simple terms, and this is why I'm saying these error messages are not incredibly useful, but what this is referring to is the fact that R is interpreting this as an instruction, some code. And this is not code, this is text. So R doesn't know what to do with this, so it just says, well, I don't know what you mean, what are you assigning to me? So error, I'm not going to do anything. And while we're here, I want to illustrate, when we catch an error, it won't run the line after it. So let's say I have lucky num set to 777. Okay. And if I go here and run, you'll see that it stops executing here. Lucky number is not run. The line with lucky number is not run yet, and that doesn't appear in the environment anywhere, which proves to us that it's interpreted. Now, we can change the value an object holds, obviously, right? And in order to do that, we just have to reassign to it. So again, I'll do my shortcut here, and I just want to illustrate to you when I do this. See, we don't get an error because it's commented out, doesn't run. So right now, my name is set to Alexander Ristic, but let's change it to our professor's name. So let's go my name, assign the value Alexander Jovic. And before I hit enter, hit enter to run it or click run, just look at our environment here. It's a character, its value is this. Run. If I hit run, say that now that's changed now to Alexander Jovic instead of Alexander Ristic. And so what that means is that we can just reassign to the same name. We can reassign what objects, the value that an object refers to. And the old name just disappears, essentially. It's thrown away, it's garbage. And now whenever we call, my name, we'll get Alexander Jovic as the output, not Alexander Ristic. We can, of course, just to be aware of this fact, we can change this to something that's not text. We don't have to change it to another piece of text. This is just a name that we use to associate a value that we find useful. So we could do something pretty illogical, like my name is 4204. And so now it's no longer character, it's numeric, and now it's 4204. And if I type in the console my name, I get the output 4204 instead of Alexander Jovic. So this just, again, goes to show you that these are just labels that are associated to the value via the assignment operator. And of course, as we've seen many times before, every change is reflected in this environment here. Now I can make this a little bit bigger. And let me just show you what happens here if I clear this. What do you think will happen now that I've cleared the environment and tried to use these names? What do you think will happen? Let's try. Let's try favorite number. And hit enter to run it. Error. Object favorite number not found. So this is an error you might encounter sometimes. And what this is saying is essentially this. Our environment is empty. So as far as R is concerned, this name does not exist. And this binding does not exist. So that when I try to access it, it just says, well, there's no object by that name, so I'm going to error out and tell you as such. So that's just something to keep in mind. Let's clear the console again just to make things a lot easier and move on to our next point. There are some naming conventions. I want to mention just two of them. If we have multiple words for an object, like for example, my area code, I can use underscores to separate the words. So my area code, or I could do something called camel case, my area code. Both of these are perfectly valid. Choose the one that you prefer. You might see me doing this one more often just because it's a little bit more legible to me, but again, this is a matter of personal preference. Now, let's go to our functions. Before I do that, I mentioned numeric types, your numbers. And there's integers as well, which are whole numbers, and then numeric, which is any kind of number. So For example, pi is a numeric. And I can illustrate that. Pi, let's say p is pi. Numeric value 3.1415926.5, and so on, repeating. It's irrational. So that's a numeric type. There's integer types, there's character types, but there's also a type called logical. And these have only two possible values, true or false. And these tend to emerge when we're checking conditions. So I'll show you what a logical value looks like. Say logical underscore value, and we'll type in uppercase true, and I'll hit run. And you'll see that its name is logical value, its type is logical, and its value is true. And we can also have logical value 2 is false. And if we run that, we get logical value 2 is another logical whose value is false. By themselves, not very useful, but in combination with functions, incredibly useful, especially when we're doing conditions. Speaking of functions, let's get into functions. But first, as a good habit of practice, let's clear our environment and clear our console before we go on. And of course, as you can see here in history, we can see everything we've done. So, R functions. What is a function? An R function is essentially or effectively a structure that holds a series of instructions that are needed to complete a task. So it's a series of instructions, a structure that holds a series of instructions needed to complete some task. So it's basically a set of instructions that tell R how to do something. For example, the mean function that's built in with R tells R, okay, take in a bunch of numbers, add them together, and divide by how many numbers there are, and that gives you the mean. Base R, this R that we're using right now, comes with a lot of functions. We've seen log, log base 10, we've seen exp, we've seen square root, I've just mentioned mean, we have other things like VAR for variance, SD for standard deviation, and so on. One of the main functions that I want to introduce to you is something called concatenate. This function you'll use so often it's not even funny. So the concatenate function, which we write as C and then pass in some values, what it does is it joins many distinct values into a single object that we call a vector. And importantly, every single element of a vector has to be of the same type. So let me just make this more concrete. Let's say I call this sample vector, or even easier, vec1. Vec1, we'll say concatenate C, open a bracket, and we'll put in here the values that we want to concatenate. So 1, 2, 3, 4, 5, 6. Okay. Run this. Okay, so we got a vector now with this name. It's a type is numeric, its length is 6, it's 96 bytes, and you see that its values are this. Let's actually print out what vec1 looks like just so we can understand this. So we can see that it contains 6 values that we specified, but all in one structure. And this points out a lot of key things, actually, more than it might be immediately obvious. First, every single R function, or most, have their name followed by a pair of round brackets. So C, opening round bracket, closing round bracket. And RStudio is actually very nice. It shows you, whenever you open one, where the closing one is, just to make sure that you're not missing brackets. These have to be here even if we don't put anything between the braces. This is similar to Python, where in order for us to run a function, we have to put in this round brackets in order to tell Python, hey, we want to run this function. We want to execute it. We want to get an output from it. The things that we provide between the round brackets are called function arguments. These are objects or values that we provide in the brackets that the function uses to run. And every single argument, as you can see here, is separated by comments. So in this case, I have 6 arguments, the numbers 1, 2, 3, 4, 5, and 6. These are all arguments to this concatenate function. And it operates on those arguments. And when I run it, what it does is concatenates. It combines them into one structure. The third thing is, and this is not immediately obvious, functions have a help document associated with them. We can just run help and then bracket the name of the function, or easier, question mark and then the name of the function. So question mark C, run that. And you'll see help pops up with C base, combine values into a vector list. And we get a description. This is a generic function which combines its arguments. I won't go in deeply into the help, but you can view help very easily and then scroll through this to see how to use it and some application areas of it. So now that we've covered that, I want to talk a little bit more about vectors, because they're a very common data structure that we use. So when we have a vector, we have essentially what we call a list or collection of numbers. When we have a collection of numbers, we can do a lot of things with them. We can find their mean, their variance, their standard deviation, the number of elements. The number of elements, by the way, is called length. And these are all functions that we can run. So I'm going to put in a comment here, which is good practice. I'm going to say testing functions on a vector. And I'll say mean, variance, standard, and actually what I'll do is this. Mean, vec1, vector 1 mean, var, vec1, vector 1 variance, sd, vec1, vector 1 standard deviation, and length, vec1. No elements in vec1. So this is very good practice. I'm going to save this as my first script. So now you'll see that when I add this space, you'll see that this changes color to indicate that I may have changed. But see here now, when we run a function, we have a comment that explains what this is doing. So that's very good practice to get used to. But let's run this. So run this. Then mean, 3.5, variance, 3.5, standard deviation, 1.870829, and length, 6. So we see that we can run a lot of functions here with this list of values and get an output that is useful. Length especially tells us 6. We can actually count that. 1, 2, 3, 4, 5, 6. Makes sense. So we can see that this works as intended. I want to cover now that we can do some other useful things, like for example generating sequences. And I want to cover 3 ways of doing that: sequence, repeat, and a shorthand with a colon. So first thing is generating sequences as a new header. And here, method 1 will be this: to generate a regular sequence. What I'll do is just do this. Say my SEQ is 1 to 10. So regular sequence. And here, what this means is starting at 1, create a sequence starting at 1 that increases by 1 all the way up to 10. So that's going to create a vector. If we save and run this line, we'll see that we have an integer sequence vector. And if I print this out to the console, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as we intended. So that's a very common shorthand if I wanted to make a sequence quickly. We can do the reverse. We can say my sequence 10 to 1. So regular descending sequence. And so now watch this. 10, 9, 8, 7, 6. And if I type in my SEQ down here, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's a nice little shortcut to make a quick vector of elements that are one greater than each other. But what happens if we want to make a vector where the elements are not necessarily one greater than one another? For that, we can use sequence. So sequence. The sequence function, I should say, sequence function. So the sequence function, what we do here is we provide a start value, a stop value, and a step value, or a from to by argument. So I'll show you what I mean by that. Let's say I want to create from 1 to 10 a list of all even numbers, numbers that are divisible by 2. So in order to do that with sequence, I'll just do this. Evens is seq for sequence, from equals 1, 2 equals 10, by equals 2. Run this. So you have this. And actually, I ended up making odds. Wow, didn't really think that through. But you see that we have a sequence here where it started from 1, it went up 2, but not including 10, it increased by 2. So we have 1, then 3, then 5, then 7, then 9. What about if we actually wanted to make it even? Well, then we can start from 2, we can go up to 10, and we go up by 2 instead of starting from 1. And if we run that again, there we are. If we open this up, 2, 4, 6, 8, 10, just as we'd expect. We also have the repeat or replicate function, just as repeat values and repeat it a given number of times that we specify. So as an example, let's say I really want to have a vector of all number 1s for some reason. So I can do this. One vector is rep for repeat. Here we're going to put in the value that we want to repeat, which is 1, and then the number of times we want to repeat it, which is, let's say, in this case, 5. And if we run that, if I print out one vector, we have 1 appearing 5 times. We can do more complicated things than that, obviously. We can repeat text if we want, or repeat a vector. So for example, let's say I really love repeating the word apple. So okay, apple vec is repeat apple times equal, let's say, 3. Run this, and if we look at apple vec, we have apple showing up 3 times in quotes. Finally, we can repeat an actual a vector directly. So I'll show this. Say repeat a vector by doing this. Say rep test is rep c 1, 2, 3 each equals 2. So let me explain before I run this. This is going to repeat every element of this vector, each element, twice. So the output should be 1, 1, 2, 2, 3, 3. Let's see if that's the case. If we look at rep test, 1, 1, 2, 2, 3, 3. Now, this might seem like a toy example, and it kind of is, but the main takeaway, especially from this, is that we can place a function within a function. We place concatenate to create a vector within the repeat function. And so what that means is that on top of accepting objects, what that means is functions are objects, which means that they can be arguments to functions. We call the fact that we can put a function inside another function nesting. And nesting, as you can imagine, lets us do a lot of complicated stuff in a very concise way. There is a caveat here, which is that nested code becomes really hard to read, especially if you get to multiple levels of nesting. This is not so bad, but imagine if I had 3 or 4 levels deep, this might be impossible to read, right? Let me very quickly just change the font size to something a little bit smaller. There we are, much better. Let me clear the environment because there's a lot of garbage here. Same with the console. And I'll move further down here. with my script. Now I want to go more into working with vectors since they are such an important data type. So the first thing I want to talk about is how do I get an element from a vector. So first of all, what the hell is an element? So every single item that's inside a vector is called an element. And every element in the vector has an index. And that index is a positive integer whole number that's assigned to each element of that vector beginning at 1. So let me show you what I mean by that. I want you to picture we had a vector like this. A, B, C, D, E. Let's say it's a vector with 5 elements, A, B, C, D, and E. In this case, the vector is this. So I'll say that's the vec, and the index, or IDX for short, in this case would be 1 for letter A, 2 for B, 3 for C, 4 for D, and 5 for E. And what we can do is to retrieve values from a vector, we can refer to these index numbers. So, as an example, let me actually create a vector here. So we'll say alphabet vec is, or just to make our life easier, vec2 is C, A, B, C, D, and E. Run that. We have a character vector. Again, let me very quickly plot that out just so you can see. We have A, B, C, D, and E. And now let's say I wanted to get the letter D from vec2. So using what we just learned, what index should the letter D be? Well, if A is number 1 in this case, then D should be index number 4. And so what that means to get D, we have vec2 4. Get 4th element, which is D. And if we run that, we do get D, in fact. So now we know how to get a specific value. We can actually get multiple values at once if we want. So how do we do that? Well, we can do that by using the concatenate function with inside these square brackets. And these square brackets are how we index. So let me say I want to get A and E, but not B, C, and D. So A is at index 1, and E should be at index 5. So then I can just say vec2, and I want to index from C, 1, 5. So get first and fifth elements, which in this case are A and E. And if I run that, we get A and E, just as you'd expect. So what we're doing here, this technique of indexing is called positional indexing. Makes sense because what we're doing is using an item's position number, its index number, to retrieve it. This is relatively common, but we can also do something called logical indexing. And what this involves is using a logical expression, so something that is either true or false, as an index to get a value from a vector. So I will show you something first, and then I'm going to explain how it works. Now, in order to do this, just to make our life easier, I'm going to create a new vector. Say vector 3. This is going to be a vector of numbers 1, 3, or actually, you know, let's use our thing 2 to 12. So 2, 3, 4, 5, 6, 7. Yeah. So then now, let's say I want to get every element from that sequence, and just to make it clear what that sequence is, let me print it out. I want to get every element here that is bigger than 8. So I would type this, vec3 greater than 8. I get 9, 10, 11, 12. So that works, but you know, what's going on here? Like, how does this work? What is happening here? This is a logical expression here. This is the actual logical expression. So let's try to look at this a little bit more. So get everything greater than 8 in vec3. Well, let's comment out this line. And let's look at this expression, vec3 greater than 8. If I run that, what do I get? I get false, 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 true, 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 true. And by the way, see how I have multi-line output now? So look at the bracket 10 here. If we count 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 10th item. So this is a bracket 10 to indicate that. So this is the 11th item. So we can see here that what R is doing when we run vec3 greater than 8 is it creates a vector that has the same length as vector 3, but where every element is either true or false. And each true or false in this new vector that's created corresponds to whether that condition, that logical condition, that expression, is satisfied for that particular element. So what I mean by that is this. We are checking element by element whether something is greater than 8. Is 2 greater than 8? It's not, so it's false. Is 3 greater than 8? It's not, so it's false. Is 8 greater than 8? No, so it's false. But what about 9? 9 is greater than 8, so that's true. And so the output of the vector is true, etc. for every single value that we have in the vector. And then what is happening here is that all R is going to do is it's going to return everything that is true from vector 3, which is why we get 9, 10, 11, 12. What that means for us, by the way, is that this is functionally equivalent to writing something like this. Vec3, C, false, 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 dot, 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 true, true, where the true values come from here and the false values come from here as well, and then just getting the trues as output. So R is doing a nice little shortcut for us where it evaluates this logical expression to get this particular logical vector and then returns only the true elements. So that's very handy, and that's something that we can do quite often and something that we can do frequently, actually. Now, we just did an expression vec3 greater than 8. So that's a logical comparison. And we did the greater than, but there's other comparisons we can do. We can do this symbol, which means less than. We can do doubles equals, which means equals. We can't do a single equals because technically you can use a single equals to assign a value. It's bad practice, but you can do it. And if you just use a single equals, it will assign a value rather than doing the comparison. We can do a left arrow and an equal to mean less than or equal. We can do a greater than and equal sign to mean greater than or equal. And we can do an exclamation mark and equal to mean not equal to a particular value. So let me show you what I mean by that. Control-Shift-C to comment those out. So vec3 not equal to 2, or not equal to 4. See what that happens. 2, 3, 5, 6, 7, 8, 9, and so on. Or as another example, let's go vec3 less than or equal to 6, let's say. Run this, and I get 2, 3, 4, 5, and 6. Now, we can actually combine these expressions using something called Boolean operators to make a lot more complicated logic. We can use the two operators that I'm going to introduce to you is the ampersand symbol here, which is equivalent to and, it means and what I'm going to call the vertical bar, which means or. And what this does is it combines two expressions and checks. And would only be true if if all logical expressions involved in it are true, or is true if any logical expression is true. So this doesn't make a whole lot of sense right now, I will admit. So let me show you what I mean by that. So let's say vec3 less than, let's try a task. I want to get all values in vec3 between 4 and 8. So in order to do that, I have an and between 4 and 8, which means I have to use my ampersand. So we would do that like this. We would index, as we usually do. We would provide a logical expression, but in this case with a Boolean operator to make it more complicated. And in this case, we'd say vec3 is greater than or equal to 4, and vec3 is less than or equal to 8. So this will create bounds for us, where we'll get every value that's greater or equal to 4, so we won't get 2 or 3. And we'll only get values of less than or equal to 8, so we won't get 9, 10, 11, or 12. And if we run this, we get 4, 5, 6, 7, and 8, as we might expect. Or, let's say, I want to get all values in vec3 that are not 2 or 12. So again, here we can do a little bit differently. We know we have to index. We're going to provide a logical expression index, but in this case, the logical expression that we want is vec3 not equal to 2 and vec3 not equal to 12. And if I run that, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's how we can use the Boolean logic to create more complicated matching to get exactly what we want out of a particular vector. Now, we can actually use this indexing to update values of a vector. So right now, let's look at vector 2. It's a character vector of just A, B, C, D, and E. Let me say I want to change the first value instead of A to be Z. So what I could do is this. vec2 1, assign it Z. See how that's now changed from A to Z, but everything else is unaffected? So this is an incredibly useful way to change a particular element of a vector. Now, remember how I said everything in a vector has to be the same data type? What happens if I do this? My vector, vec2, index 2, 30. Run. Well, isn't that interesting? What happened here? We see 30 showing up, but it's not showing up as a number. It's showing up as a character. So what R is doing for us is trying to be our little helper. Effectively, what it's doing is when we try to assign this value here, it looks and says, this is a character vector. You're assigning 30 to it. Can I convert 30 to a character? I can. Okay, let me convert it to a character implicitly in the background, and then assign it to that value, to that index, instead of B, and everything works as intended. If we can't do this conversion, if it tries to do something it can't do, it'll create an error. But this is just something to keep in mind. This is not great practice because we're expecting R to do something indirect for us. I want to quickly mention that we can use some functions in vectors. We've already seen examples, but let me show you one of sorting a function, sorting a vector in an ascending, so lowest to highest. So let's consider a new vector. Vector 3 is already sorted, but let's say vector 4 concatenate 3, 1, 5, 2, 9. Okay, something that's got a random order to it. It's not ordered. So now, if I go sort vec4 and run it, I get 1, 2, 3, 4, 1, 2, 3, 5, 9. And if I can actually do sort vec4 decreasing equals to true, and this will do a largest to smallest ordering. 9, 5, 3, 2, 1, as we'd expect. Now, that's all I really want to talk about immediately right now for vectors. The next topic is related. It's something called vectorization. Excuse me. So, most R functions are vectorized. And I'll start a new section here. Vectorization. So, let's create some room here. So most R functions are vectorized. What does that mean? That means that the function will work on every single element of the vector, and we don't have to run the function for every element ourselves. So, a very simple thing to illustrate this is, look at vec4. It's a vector with 5 numbers. It's numeric. What happens when I run vec4 times 10? Let's say vec5 is vec4 times 10. Have a look at vec5. 30, 10, 50, 20, 90. So you'll see here that for every single element of vector 4, it multiplied that by 10, and it moved to the next element. It multiplied that by 10, and next element it multiplied by 10, and it did that per element without us having to say something like vec4 at 1 times 10 and vec4 at 2 times 10. It just did that for us automatically. This, you can see, also applies to if we added 2 vectors. So let's try vec4. Vec sum is vec4 plus vec5, and vec again is short for vector. Have a look at vec sum. 33, 11, 55, 22, 99. Where's 33 coming from? 3 plus 30. Where's 11 coming from? 1 plus 10. Where's 55 coming from? 5 plus 50. So you see that it's doing a piecewise addition of each vector. It's the same thing as doing this. If I listed out the values of vec4 and vec5 and vec sum, we would have, for example, vec4, the first value in vec4 is 3. The first value in vec5 is 30. So the sum would be 3 plus 30, which is 33. The second value of vector 2 is 1. The second value of vector 5 is 10. So then the vector sum should be 1 plus 10, or 11. And we can continue this all the way down. Now, the logical question that should come to your mind is, okay, what happens if you try to do something with 2 vectors that have different lengths? So, as an example, vector 3 has a length of 11, vector 4 has a length of 5. What would happen if I added vector 3 and 4 together? What would the result be? Let's try it out. Let's say vec sum 2 is vec 3 plus vec 4. You'll say R is going to give us a warning. Longer object length is not a multiple of shorter object length, but we still get an answer here. And if I have a look at it, the length of it is 11. So what's happening here? What's happening here is a sort of implicit in behavior in R called recycling of vectors. So what that means is R will try to repeat the smaller one to try to match the length of the longer one in order to do this vectorization that it does. So in this case, for example, vector 4 has 5 numbers. Vector 3 has 11. So what R is going to do effectively is repeat vector 4 3 times, essentially. So in this case, just to make this more clear, and it'll do that and then do the sum, just to make it more clear. Let's go vector 3 values, vector 4 values, and then vec sum 2 values, like we did above, just to make it clear. So vector 3 first values 2, 3, 4, 5, 6, 7. If I hover over it, I should get it. Yep, 8, 9, 10, 11. Okay. Vector 4's first values 3, then 1, then 5, then 2, then 9. So up to here, nothing is unusual. But at this point, at this line here, R is going to recycle vector 4. So this will become 3. This will become 1. This will become 5. This will become 2. And that will become 9. And there's number 12 here, and this will repeat again to be 3 in order to match the length. And so this becomes 2 plus 3, which is 5. This becomes 3 plus 1, which is 4. This becomes 4 plus 5, which is 9. And that's all normal. But then if we look here, this should be 7 plus 3, which is 10. And that occurs in 1, 2, 3, 4, 5, 6, position 6. And if you look at position 6, 1, 2, 3, 4, 5, 6, we see 10. Then position 7 is 9, which is 8 plus 1. And so we see this recycling behavior happening, which is explaining why we get this output. Now, again, this is an implicit thing R will do. We do not want to rely on implicit things because it can produce some unexpected results. And especially if you're not familiar with this behavior, it's not really intuitive for it to happen. If you ever want to do an operation on a vector, on two vectors, try to make them the same length. Even if you have to fill them with empty data, just to make sure the lengths are the same in order for recycling to be avoided so we don't get any unusual answers. Now, I want to briefly talk about some things about getting help. In order to get help, we can type in, getting help. So in order to get help, if we know the name of a function that we want help with, we can type in help and then put in the name of the topic or the function. So for example, let's say help, in quotes, SD for standard deviation. Run that. It'll open up SD from stats standard deviation page. It'll have a description of what it does, how to use it, the arguments that it expects, and a description of those arguments, its details, related functions, and examples of how to use it. Or alternatively, we can run this. It'll open up the same thing. But a third thing we can do, which a lot of people don't know, is let's say I know something related to the topic, but not the specific name of the topic. So for example, let's say I know I'm doing something related to a mean, but it's not the mean function. What I can do then is run help.search mean. Check this out. This should open, eventually, a search results page that has any help pages that are related to mean. For example, k-means or EMM grid. These are libraries that I can click on, and each of these links I can click on to find maybe what I'm after. As an alternative to run the same thing, I can do $? mean, and it'll open up the same exact page, and I can search for things. And let's say I wanted stats k-means. I click on it, and now I get k-means clustering, and I can look into that if that's what I was after. Another huge thing you can do for help is the function RSiteSearch. We can search for something, and it'll take us directly to the CRAN website for information. So, logistic regression. Run this. And you'll see that it opens up automatically for me. Logistic regression search here. And I'll have a bunch of results here. And if I go back to RStudio, you'll see a search query has been submitted to this URL, and the results page should be opened in your default browser shortly. So that's another useful thing we can do to get help. There are other sources of help, of course. There's Google, there's Stack Overflow, there's various GPT models, Gemini, ChatGPT, Copilot, and so on, Claude. and a bunch of reference sheets. The final thing I want to mention here as a quick thing, just so we know, if I want to get the data type of something very quickly, I can use the class function. So class 30, numeric, class applesauce, character, class true, logical, class C31297, numeric. See, this is numeric because all its arguments are numeric. And so this gets us very easily the type of thing that we're working with. We can also see it on grid view like we have here, but if we're in list view, we can also see it as well, just in a more abbreviated fashion. So that should cover the introduction to R and RStudio and the sort of essential components. I'm going to make a second video where I talk about loops and conditional statements and branching structures, because I think those are important to know. And then I'll also make a third video where I talk about how to do Monte Carlo simulations. And in that case, I'm just going to cover sort of the logic behind how to approach the problems, just so you have a good understanding of how to do assignment number 0.